Good morning. Let us start general microbiology. The first topic will be the history. Among history, I will discuss the important eminent microbiologist. To start with, Louis Pasteur. Louis Pasteur, again, he is known as the father of microbiology. He has contributed various things, like he has discovered the method of pasteurization of milk, fermentation principles, he has also laid down the germ theory of life, various sterilization principles like autoclave, hot air oven, all this, the basic principle was laid down by Louis Pasteur. He has discovered the various vaccines like cholera vaccine, anthrax vaccine, rabies vaccine, not the vaccines which are in use now, but the first stage of the vaccines for cholera, anthrax and rabies are discovered by Louis Pasteur. Of course, now those are much modified and the later advanced vaccines are used. So these are the various contributions laid down by Louis Pasteur. And the second eminent microbiologist is Robert Koch. Robert Koch. And he is also very popular in the field of microbiology. Many authors, they name Robert Koch as the father of modern microbiology. He has also laid down various principles, like he has used solid media for use of bacterial culture. He has first time he has isolated bacteria in pure culture. He has developed the concept that we can isolate the bacteria in pure culture. Hanging drug for bacterial motility demonstration. Again, the principle was laid down by Robert Koch. He has also introduced the staining technique. He has told that by staining we can demonstrate the bacteria in much better way. Aniline dye he has used first. Aniline dye he had used first. And the most popular discovery of Robert Koch is Koch postulate and Koch phenomenon. First I will tell you about Koch phenomenon. It was demonstrated in tuberculosis. They say that injection of the TB antigen, crude TB antigen in susceptible guinea pigs leads to development of induration. Induration of crude tuberculous antigen in susceptible guinea pigs leads to development of induration, which he has named as Koch phenomenon. What is Koch postulate? Koch postulate was the most important contribution of Robert Koch. Koch postulate tells about the association of a bacteria with a disease. It says that a microbes is said to be linked with a disease, said to be the causative agent of a disease, if four criteria are fulfilled. The first criteria is the microbes should be constantly associated with the disease. There should be a constant association of the microbes with the disease. Second is you should be able to isolate the microbes from the clinical sample. From the clinical sample of the patient, you should be able to isolate the microbe. When you inject the microbe into experimental animal, it should produce similar disease. and you should be you should be able to re-isolate the microbes from the experimental animals. You should be able to re-isolate the microbe from the samples of experimental animals. So these are the four postulates under Koch postulate. Later on, the fifth criteria was introduced by his followers, and according to this, they say that there should be antibody production also against the microbes. Against the bacteria, there should be antibody production. So serological response is the fifth criteria which was introduced later. Of course, now molecular Koch postulate has been laid down. Currently, molecular Koch postulate has been laid down, and according to this, it is the gene of the microbe rather than the microbe per se which should be constantly associated with the disease. According to this, it is the gene of the microbe, it is a virulent gene of the microbe rather than the microbe per se should be constantly associated with the disease manifestation. So this is about molecular Koch postulate. Okay, so these are the various contributions by Robert Koch. Then we can discuss the third eminent microbiologist, that is Paul Ehrlich. Paul Ehrlich again has laid down various contributions, like he is the inventor of acid fasting. He is also known as father of chemotherapy, as he has discovered a drug called as salvarsan for the treatment of syphilis. The salvarsan was a drug which was called as magic bullet because it was the first drug which was used for treatment of infectious disease. Hence he was known as father of chemotherapy. He has also introduced the side chain theory of antibody production. Ehrlich phenomena, which is a toxin antitoxin phenomena, especially demonstrated for diphtheria toxin. This was experimented on diphtheria toxin, so it was known as Ehrlich phenomenon. Ehrlichia is a rickettsia group of microorganisms which was named after Paul Ehrlich. Ehrlichia. Okay, so these are the various contributions of Paul Ehrlich. Other contributors like Edward Jenner, he was known as the father of vaccinology. He had discovered the first vaccine, that is vaccine for smallpox, by using cowpox. He has used cowpox strains, cowpox virus, to vaccinate against smallpox. Other important contributors like Anthony von Leeuwenhoek. He is the inventor of simple microscope. Then Ruska. Ruska is the inventor of electron microscope. Electron microscope. Carey B. Mullis. Carey B. Mullis is the inventor of PCR, polymerase chain reaction. John Kohler is the inventor of monoclonal antibody. He has discovered monoclonal antibody. So these are some of the important contributors in the field of microbiology which you can remember. There are various organisms which are named after the microorganisms, the microbiologists. Like for example, Koch-Wick bacillus. Yes, Haemophilus aegypticus. So there are various organisms named after the discoverers. Then Klebsiella bacillus, Corynebacterium diphtheria. Okay, Eaton's agent, Mycoplasma, Pfeiffer's bacillus. The detailed list is there in your book. You can have a look. I am just outlining the important ones. So it is the Haemophilus influenza, which is called as Pfeiffer's bacillus. Okay, so there are various microorganisms named after the discoverers. Fine. So this is all about history. Then I will tell you a bit about bacterial taxonomy. There are three ways the bacteria can be classified. They say that the classification of bacteria can be done by three ways. The most conventional method is phylogenetic classification. According to phylogenetic classification, they say that it is a branching tree-like classification. It is a hierarchical arrangement of the microorganism resembling a branching tree-like pattern. At each node, there is a weight character to classify. Like for example, the bacteria can be classified based upon the shape into cocci and bacilli. Each based upon the gram stain, you can classify into gram positive and gram negative. Gram positive cocci, gram negative cocci, gram positive bacilli, gram negative bacilli. So the shape of the bacteria has a higher weightage than gram staining property of the bacteria. So this is called as a hierarchical classification of the bacteria resembling into a branching tree-like pattern. And at each node there is a character to classify the bacteria, and each character having a particular weightage. So this is the most popular and this is the most practical classification. Later on, there was one more classification introduced called as phonetic classification. Phonetic or Addisonian, as it was discovered by Michael Addison. Hence, it was called as Addisonian classification or phonetic classification. According to this, it has given all characters equal weightage. They say that why to give more weightage to a particular character? It may be arbitrary because this weighing characteristic is totally arbitrary. Whichever character you are thinking having more weightage, you just blindly give more weightage. So why to give arbitrarily more weightage to some character and less weightage to some character? So according to this phonetic or Addisonian classification, all characters are given equal weightage, and this classification is basically used in numeric taxonomy. Taxonomy. And the third and the most acceptable classification is molecular classification, which classifies the bacteria based on the genetic constitution of the bacteria. So coming to microscopy, a good microscope would depend upon three properties. It should have a good magnification, good contrast, and good resolution. The magnification of the microscope can be enhanced by using lens, especially the concave lens. If you use, it will increase the magnification. Contrast of the microscope can be enhanced by using staining, as well as if you use phase contrast microscope. This also increases the contrast, enhances the contrast. The resolution is nothing but it is the ability of the microscope to differentiate two objects as two separate points. Ability of the microscope to differentiate two closely placed objects as two separate objects. So the resolution of the microscope, they say that the resolution power of human eye is around 0.2 millimeter. The resolution power of simple microscope is around 0.2 micrometer, whereas that of electron microscope is around 0.2 to 0.5 nanometer. So this is how the resolution power is there for various microscopes. And the resolution power is directly proportional to the refractive index of medium. Is directly proportional to the refractive index of medium, and the refractive index of oil is greater than air. That is why we use oil in oil immersion field. Okay, the purpose of using oil in oil immersion field is to enhance the resolution, because oil has a greater refractive index than air. So in a nutshell, lens are used to enhance the magnification, staining for enhancing the contrast, oil for enhancing the resolution power of the microscope. Fine, so these are the basic property of a microscope. Then coming to various microscopes, light microscope is the simplest one. They say that the light microscope, the background will be bright and the objects appear dark in light microscope. In contrast, dark ground microscope, the background is dark, whereas object to be focused appear bright. And dark ground microscope has various applications, like it is used to demonstrate the thinner bacteria, especially spirochetes, which are extremely thin, cannot be demonstrated by light microscope, that can be demonstrated by dark ground microscope. As well as bacterial motility and other important properties can be demonstrated by dark ground microscope. Living structures, they say that the living bacteria can be demonstrated, in contrast to staining, which will kill the bacteria. Next is phase contrast microscope. Phase contrast microscope, what it does is it enhances it exploits the property of contrast to demonstrate the objects. They say that the differences in contrast between water and bacterial cell, this property is exploited to demonstrate the bacteria in the sample. And so this is again a microscopy method that enhances the contrast to demonstrate the bacteria. And the use of phase contrast microscope is again, it is helpful to demonstrate the bacteria in living stage. See, the contrast is also exploited by staining. Staining is again a method to enhance the contrast. But what happens is, if you stain the bacteria, it will die. Whereas phase contrast microscope demonstrate the bacteria in the living stage. It is also useful for demonstrating the bacterial motility. Bacterial shape can be demonstrated, and various internal structures like inclusions, spores, all these are demonstrated by phase contrast microscope. Fine. Then coming to fluorescent microscope. Fluorescent microscope, they say that what it does, they say that any fluorescent object or any object coated by fluorescent dye, if you subject it to ultraviolet rays are having low wavelength ultraviolet ray. When it focuses on the fluorescent objects, then it gets converted to longer wavelength of visible rays, so that you can visualize the object. Okay, very simple principle. When the fluorescent dye or fluorescent object is subjected to ultraviolet rays of low wavelength, the low wavelength ultraviolet rays gets excited and gets converted to longer wavelength visible rays, and that is how you are going to visualize the object. And this fluorescent microscope has got various applications. It has got various applications. They say that first is autofluorescence. If the object or if the bacteria itself is autofluorescent in nature, then also can be seen by fluorescent microscope. Example is cyclospora. There are various bacteria or parasite which can be stained by fluorescent dye. For example, QBC, quantitative Buffy coat examination, is a method where we use acridine orange dye to stain malaria parasite, Plasmodium. Similarly, auramine phenol staining is used. Auramine is a fluorescent dye used to stain Mycobacterium tuberculosis. So these organisms are not self-fluorescent in nature, but if you use a fluorescent dye to stain them, you can demonstrate the organism. But here again the problem is they are non-specific. The staining will be non-specific in nature. Hence the next application is immunofluorescent microscope, immunofluorescent assay. In this, the fluorescent dye tagged with antibody or the fluorescent dye tagged with antigen. This is used to demonstrate the antibody in the sample or demonstrating the antigen in sample. So this is the next application, that is tagging the fluorescent dye with antibody or antigen so that it will detect the respective antigen or antibody in the sample, and this will be specific in nature in contrast to just using a fluorescent dye which may be non-specific. Okay, so these are the various applications of fluorescent microscope. Next is the most advanced microscope, that is electron microscope. Electron microscope, it is different than light microscope by various methods. They say that light microscope has a magnification of 100 to 1000, whereas electron microscope has a magnification of more than 1 lakh magnification. The resolution power is of light microscope is around 0.2 micron, whereas electron microscope it is 0.5 nanometer. Okay, it has a better resolution than light microscope. Of course, the medium will be air, in contrast to electron microscope where the medium is vacuumed. The slide on which the object is focused, the bacteria is mounted. That slide is usually a glass slide for light microscope, whereas for electron microscope it will be a metal slide. Usually it is copper slide. And the lenses also, electromagnetic lens is used, in contrast to concave lens used for light microscope. Okay, so these are the various, and the source of energy will be light. Source of energy will be light beam, light source for light microscope, whereas it is electron beam will be the source of energy for electron microscope. Okay, so these are the various differences. Electron microscope is of two types: transmission electron microscope and scanning electron microscope. Transmission electron microscope is, it is transmitted into the object. So here internal structures are visualized. Whereas scanning electron microscopy, it usually scans the surface. Hence the surface is visualized. It is used to demonstrate the surface of the object, whereas transmission electron microscopy is used to demonstrate the internal structure. It gives a two-dimensional view in contrast to scanning electron microscope, which gives a three-dimensional view. Okay, so these are the various differences. Transmission electron microscope is the most common electron microscope used. So I will just outline how to do the specimen preparation, because specimen preparation for electron microscope is very popular, is very important for your exam. They say that for specimen to be prepared, just like that the clinical sample you cannot mount on the metal slide. They say that you have to prepare thin slices, because electron microscope can only be used when the thickness of the smear is very thin. So to prepare this thin specimen, first thing what you have to do is you have to fix. Fixation of the specimen is done by adding with glutaraldehyde, followed by you have to completely dehydrate the specimen. This is done by adding with various solvent like acetone or alcohol. Please remember, complete dehydration is must for electron microscope. Why? Because the third step is you have to add the specimen, you have to embed with plastic polymers. The next step is after the specimen is completely dehydrated, you have to add with plastic polymers so that the specimen gets hardened. Once it is hard in nature, the next is you have to do slicing. You have to do cutting of the specimen by using specific knives, electrotone knives you can use. Okay, so this is used to make thin slices. You can cut the specimen into thin slice so that it can be mounted on the copper slate. So that it can be mounted on the metal slide. So this is how you have to prepare the specimen. Once it is prepared, there are various ways to once the smear is prepared on the slide, there are various methods to demonstrate. You can do staining. This is the basic one. You can do negative staining also. You can do shadowing. Shadowing means you have to stain at 45-degree angle. Staining is done at 45-degree angle so that only a portion gets stained. And the most advanced version is is called as freeze etching technique. Freeze etching technique, where you have to totally cut the surface so that the internal structures are visualized. So these are the various applications. These are the various methods to demonstrate the mounted slide by electron microscope. So coming to bacterial morphology. So before that, just I want to summarize the differences between prokaryote and eukaryote. Of course, this is a basic knowledge you all will have. Prokaryotics examples are bacteria and blue-green algae, whereas eukaryotic are the parasites, fungi. And viruses are so primitive that they are below the characteristic of prokaryotes. Okay? Viruses, the properties are so primitive that they are less than, they are not fitting to even the prokaryotes also. They are less than the status of prokaryotes. What are the differences between pro and eukaryotes? Prokaryotes, they say that they will have cell wall composed of peptidoglycan layer, whereas eukaryotes will have cell membrane. made of sterols. Cholesterols are there. So the only bacteria to have sterol is Mycoplasma. Mycoplasma do not have cell wall. Instead of that, it has sterol in the cell wall. They don't have peptidoglycan layer. Prokaryotes, there is no cellular organelle except that they have ribosome, and the ribosome is 70S in nature, whereas eukaryote they have all the cellular organelle including the ribosome, which is 80S in nature. The respiratory organelle is mesosome in prokaryote. Mesosome are the invagination of cell membrane of the bacteria which acts as respiratory surface, whereas mitochondria are the respiratory organelle for eukaryote. So these are the differences, and coming to the nuclear differences, there is no clear-cut nucleus. There is a diffuse nucleus called as nucleoid in prokaryotes. Prokaryote, the nucleus is diffuse, called as nucleoid, and it contains only one chromosome, which is composed of double-stranded circular DNA, and there is no nuclear membrane, there is no nucleus, nucleolus, as well as there is no ribonucleoprotein. All these are absent in prokaryotes. There is no nuclear membrane, there is no nucleolus, there is no ribonucleoprotein. So these are the basic differences between a prokaryote and eukaryote, and all the bacteria are prokaryote, whereas parasites and fungi are eukaryotes. Okay, so let us now discuss the various morphology of bacteria. What are the different size and shape? Bacteria can be arranged in various shape and shape. Let us discuss based upon the gram stain and the shape of the bacteria. Can be gram positive cocci, gram negative cocci, gram positive bacilli, and gram negative bacilli. So gram positive cocci arranged in cluster, Staphylococcus. Arranged in chain, Streptococcus. Arranged in pair, lanceolate shape, Pneumococcus. Whereas arranged in pair but spectacle eye appearance, this is Enterococcus. Arranged in tetrad is Micrococcus. Arranged in octet is Sarsinia. Okay, so these are the various arrangement of gram positive cocci. Gram negative cocci are usually arranged in pair. They are always arranged in pair. If it is kidney shaped, Gonococcus. If it is lens shaped, it is Meningococcus. Meningococcus. So this is the arrangement of gram negative cocci. Then let us discuss gram positive bacilli. Gram positive bacilli can be arranged in chain. Example is Bacillus anthracis, where it is called as bamboo stick appearance arrangement. Bamboo stick appearance arrangement. It can also be arranged in Chinese letter arrangement, also called as cuneiform arrangement. Example is Corynebacterium diphthery. Palisade arrangement, that is other Corynebacterium species called as diphtheroids. Diphtheroid, they have a palisade arrangement or they are parallel to each other. Okay, gram positive bacilli can be arranged in branching pattern. Branching filamentous gram positive bacilli examples are Actinomycetes, which includes Actinomyces and Nocardia. Actinomyces and nocardia are under actinomycetes, which are arranged in branching gram-positive bacilli. Okay, so these are the various arrangement of gram-positive bacilli. Similarly, gram-negative bacilli can be arranged in various ways. Curved gram-negative bacilli like Campylobacter and Helicobacter. Campylobacter has a typical gull-wing appearance. Similarly, coma-shaped bacilli, Vibrio, giving rise to fish in stream appearance. Fish in stream appearance, coma-shaped bacilli. Okay. Then in chain, gram-negative bacilli in chain is Streptobacillary moniliformis. Streptobacillary moniliformis. Pleomorphic. Pleomorphic means various size and shape. Pleomorphic gram-negative bacilli. Proteus, Haemophilus influenza, all these are pleomorphic. They have different shape and size. Thumbprint appearance. Bordetella. Bordetella, arranged in thumbprint appearance. Spirally coiled. Spirally coiled if they are flexible. Example is spirochete. If the spirals are rigid spirals, example is spirillum. Okay, so these are the various size and shape of bacteria. Now we will discuss the bacterial morphology, that is the different component of bacteria. To start with, bacterial cell wall. Bacterial cell wall. What is the difference between a gram-positive cell wall and a gram-negative cell wall? They say that the bacterial cell is composed of peptidoglycan layer. The main component of bacterial cell wall is peptidoglycan layer, which is very thick in gram-positive, maybe around 100 layer thick in gram-positive, whereas in gram-negative it is the peptidoglycan layer is very thin. Okay. Other differences like teichoic acid is a part of gram-positive cell wall, whereas gram-negative cell wall, the teichoic acid is absent. In place, it has got lipopolysaccharide layer, which has components like lipid A, which is also called as bacterial endotoxin, and the somatic antigen or the O antigen or the somatic antigen. So these are the component of lipopolysaccharide. Apart from that, it also has various aromatic amino acids. Aromatic amino acids are absent in gram-positive. They are present only in gram-negative. So coming to the peptidoglycan layer, the structure is like this. Peptidoglycan layer is composed of several layers. In gram-positive, there are almost 100 layers, and each layer is composed of alternate NAG and NAM molecules. I just write G and M. NAG stands for N-acetylglucosamine, NAM stands for N-acetylmuramic acid. So like that there are 100 layers are there, and from each NAM molecule there is a tetrapeptide side chain. From each NAM molecule there is a side chain arises, which is composed of 4 amino acids. So tetrapeptide side chain. So this part is common in both gram-positive and gram-negative. The difference is in gram-positive, in gram-positive, at the third position of the tetrapeptide chain, there is L-lysine. Compared to gram-negative, where the third position there is diaminopymatic acid. diaminopymidic acid. So this is one difference. And the second difference is both the tetrapeptide side chain in gram positive are joined together by a pentaglycine bridge. Please remember, both the tetrapeptide side chain in gram positive, they are joined by a pentaglycine bridge, and the bridge is absent in gram negative. They say that both the side chains are just directly joined to each other in gram negative. They say that in gram negative the pentaglycine bridge will be absent, and both the side chains are directly joined to each other. So that is the difference between gram positive peptidoglycan and gram negative peptidoglycan. Now we will discuss about the other component of bacterial cell. So flagella and capsule. We can start with capsule. Capsule is the glycocalyx substances released outside, and if it is, they say that it is extracellular glycocalyx like substances released by the bacteria, and it forms a layer outside the bacterial cell wall. If it is well organized, it is called as capsule. If it is loosely formed, it is called as slimelet. Loosely formed, it is called as slimelet. And the main function of the capsule is it prevents the bacteria from phagocytosis. It prevents the bacteria from phagocytosis. This is the main function of the capsule. Apart from that, it also helps in adhesion. And they say that at times bacteria can form biofilm because of the capsule. So they say that this is the bacterial cell, and if the capsule is well organized, it is called as capsule. If it is loosely formed, it is called as slimelet. And biofilm is nothing but the capsule of adjacent bacteria, they merge to each other. They say that this biofilm is usually found on plastic surface. So wherever any device is there inside the body, like for example catheters, ventilator tubes, central lines, or even the stitches, sutures, IV shunts. So any devices, if they are there inside, any plastic devices are there in the body, bacteria tend to form biofilm on the plastic surface, and the biofilm is nothing but it is the coalescence of the adjacent bacterial capsules. Millions of bacteria, the capsules get merged to each other, and the bacteria will be embedded inside. Bacteria will be embedded inside, and this kind of biofilm helps in adhesion to the plastic surface. It helps in adhesion and invasion to the plastic surface. First property, and also it prevents the antibiotic entry. It also prevents the antibiotic entry. The antibiotics are not allowed to enter inside, and that leads to bacterial resistance. So it is one of the method of bacterial drug resistance. Okay, so biofilm is another important function of capsule. Okay, there are various examples of capsulated bacteria. The capsulated organisms, example, mostly the capsule is composed of polysaccharide. Most of the capsules are composed of polysaccharide. Example is pneumococcus, meningococcus, H. influenza, VI polysaccharide capsule of Salmonella typhi. All these are polysaccharide capsules. Klebsiella pneumoniae, again one more example. Sometimes Pseudomonas also, not always, but some strains of Pseudomonas. Whereas capsule is polypeptide in nature. Here the one and only example is Bacillus anthracis. Bacillus anthracis, the capsule is polypeptide in nature. Capsule can be hyaluronic acid. It is composed of hyaluronic acid capsule is present in Streptococcus pyogenes. Streptococcus pyogenes, the capsule is composed of hyaluronic acid. And the only fungi to be capsulated is Cryptococcus neoformans. Cryptococcus neoformans also has a polysaccharide capsule. It is the only fungus to be capsulated. How to demonstrate the capsule? You can demonstrate the capsule by various means. Like, for example, you can do Quellen reaction. Quellen reaction is done to demonstrate a pneumococcal capsule. Pneumococcal capsule is demonstrated by Quellen reaction. McFadden reaction. This is done to demonstrate anthrax capsule by adding a stain called as polychrome methylene blue stain. Polychrome methylene blue stain. Indian stain. The most popular method to demonstrate the capsule is by negative stain. Example is Indian stain. Where the capsule will stand out and the background will be black. It's an example of negative stain. And of course, latex agglutination test. Latex agglutination test can also be done by using the anti-capsular antibody coated with latex particles. This is the best method to demonstrate the capsule. This is the best and the most confirmatory method to demonstrate the capsule. Okay, so these are the various ways for demonstration of capsule. Next we will discuss flagella. Flagella is the organ of locomotion. It helps in bacterial motility. Flagella are around 5 to 20 micron in length and it has got three parts. It has got a base and a hook and a filament. So like that it has got three parts. It has a base by which it is attached to the bacterial cell wall and a hook through which the filament arises. Okay, so it has got three basic components and it is an organ of locomotion. It is also antigenic in nature. And anti-flagellar antibodies are protective. I mean, they are used for diagnostic. Anti-flagellar antibodies are sometimes they are protective, not always. But please remember they are of topmost diagnostic importance. They are used for diagnostic. Like for example, H antibodies are detected in case of enteric fever by the Vidal test. Okay, so they are of diagnostic importance. There are various arrangement of flagella. Like for example, peritrichous flagella. That is, flagella arises all over the body. Example is E. coli, Salmonella, etc. Peritrichous flagella, that is, flagella arises all over the body. Polar flagella. Polar or monotrichous flagella, that is, flagella arises only from one pole. Single flagella at one pole. Example is Vibrio, Pseudomonas. Monotrichous or polar flagella. Then amphitrichous flagella and lophotrichous flagella. Amphitrichous and lophotrichous flagella. Lophotrichous flagella is tougher flagella at one pole. Amphitrichous flagella is flagella may be there at both the poles. Either single or tougher flagella at both the poles. Lophotrichous flagella spirillum. Amphitrichous flagella, the example is alkaligenous. Alkaligenous. Okay, so like that there are various arrangement of flagella. Next is what are the various types of motility. As I told you, flagella is the mean of motility of the bacteria. So what are the various bacterial motility that can be asked in the exam? Yes, tumbling motility is seen in Listeria. tumbling motility is seen in Listeria. Darting motility is seen in Vibrio. Apart from that, Campylobacter. Sometimes Aeromonas can also have darting motility, but the most important example is Vibrio. Okay, stately motility is seen in Clostridium. Swarming is a specialized motility seen by Proteus. Apart from that, Clostridium titani and Vibrio parahemolyticus. Okay, so these are the various motility. Then lashing motility, cork screw motility, all these are seen by spirochetes. And please remember, spirochete is the only example where you will have endoflagella, that is flagella present inside the cell wall, endoflagella. Okay, so let us now discuss the other important areas, that is how to demonstrate the flagella. Flagella can be demonstrated by various methods. Flagella can be demonstrated by various methods. First is by using staining technique like tannic acid stain. Apart from that, various microscopic method in electron microscope, phase contrast microscope, background microscope, all that can be done to demonstrate the flagella. Otherwise, so these are the direct method to demonstrate the flagella. Indirectly, you can demonstrate the flagella by demonstrating the motility. If the bacteria is motile, it is indirect mean to say that the flagella are present. There are various ways to demonstrate the motility. The best method is Craig's tube method. Craig's tube method. Most commonly done method is hanging rod. Apart from that, other methods like various semi-solid media can be used. For example, mannitol motility medium. Mannitol motility medium is an example of semi-solid medium, as there are various other semi-solid media also can be used to demonstrate the motility. You will also detect the flagellin, which is the gene responsible to code for flagella. That also can be demonstrated by detecting PCR. Okay, so these are the various means of detecting the flagella. Next is fimbria or pilus. Pilus is singular, pili is plural. They are hair-like appendages, much smaller to flagella, around 0.5 micrometer in length, much smaller to flagella, and they are organ of adhesion. They help in adhesion. They say that if the flagella will be like this, then fimbria will be like this. They are much smaller to flagella, hair-like appendages, and their main function is they help in adhesion. Apart from that, rarely there is a flagella called as there is a fimbria called as sex fimbria or sex pilus. This helps in formation of conjugation tube that is responsible for bacterial gene transfer by conjugation. Okay, so this is the sex fimbria or sex pilus. How to detect the fimbria? You can detect the fimbria by electron microscope. Other than that, various indirect means is that like fimbria can form surface pellicle. On the surface of the liquid medium, the fimbria can form surface pellicle. Fimbria can agglutinate with RBC. So heme agglutination reaction can be done to detect the fimbria, because fimbria has a property to get agglutinated to the various surface receptors of RBC. Okay, so these are the various methods to detect the fimbria. Fine. Now there are various inclusions. So There are various inclusions or the storage granules produced by the organism. Inclusions are nothing but they are the storage granules produced by the bacteria, which can be classified as organic granules and inorganic granules. Inorganic granule, the example is volutine granule or metachromatic granule seen in Cyanobacterium diphtheria. Volutine or metachromatic granules seen in Cyanobacterium diphtheria. Various organic granules like starch, glycogen, lipid granules, all these are examples of various organic granules. Fine. There is something about L form. L stands for Lister Institute, London. And this is the cell wall deficient form of the organism discovered by the scientist Kleinberger in Lister Institute, London. It is a cell wall deficient form of the organism. They say that irrespective of the original size and shape, if you remove the cell wall, it becomes spherical in nature. The bacteria becomes spherical in nature if you remove the cell wall. And if you remove the cell wall, the bacteria becomes spherical, and as the cell wall is not there, the bacteria will be resistant to the various cell wall acting antibiotic. So please remember, it is a mean of showing bacterial drug resistance, because L form is a form where the cell wall acting antibiotic will not work. From gram positive organism, if you remove the cell wall, the L form is called as protoplast, whereas the L form of gram negative bacteria, if you remove the cell wall, the L form what is formed is called as spiroplast. Okay, so protoplast and spiroplast are the L form of gram positive and gram negative bacteria. In presence of antibiotic pressure, usually the bacteria, they lose the cell wall to form L form. But on removal of antibiotic, they revert back to the original size. This is called as unstable L form. This is called as unstable L form, and this is the most common form of L form, because most of the bacteria, they lose cell wall in presence of antibiotic pressure, and when the antibiotic is removed, again they will revert back to the original size. So this is called as unstable L form. If the bacteria remain the cell wall deficient form for constantly, it is called as stable L form. And mycoplasma may represent stable L form of bacteria, but it is not confirmed yet. It is a controversial matter because many authors they oppose to say that mycoplasma is a stable L form, because the opposition is because mycoplasma, the cell wall is absent from the beginning. In contrast to the definition of L form, L form is defined as the normally appearing bacteria. When they lose their cell wall, they transform into L form. In contrast, mycoplasma, they are in a cell wall deficient form right from the beginning. Hence, it is a controversial issue to say that it is L form or not. So this is all about various structure of bacteria. Now we will discuss about the physiology of bacteria. What is generation time? Generation time is the So coming to the physiology of bacteria, what is generation time? Generation time is the population multiplication time. It is a minimum time for the bacteria to divide and multiply into double the number. So the generation time of most of the bacteria is around 20 minutes. E. coli and most of the other bacteria, the generation time is around 20 minutes. In contrast, Mycobacterium tuberculosis and Mycobacterium lepra, the generation time is around 15 hours and around 15 to 20 days. So this is the difference. 20 minutes, 20 hours and 20 days, like that you can remember. The generation time of E. coli is the shortest. Coming to bacterial growth curve. Bacterial growth curve is a curve which determines the viable and the total count of the bacteria when it is grown in a liquid medium. So when bacteria grow in a liquid medium, the growth occurs under 4 different phases. The first phase, when you inoculate bacteria into a medium, first phase is called as lag phase, where the bacteria doesn't multiply. I'll tell you the differences. First, there is a lag phase, then there is a log phase or exponential phase, then there is a stationary phase, then there is a decline phase. Okay? Lag phase, the bacteria doesn't divide, neither it dies. It is a phase where the bacteria forms the metabolic enzymes so that it will divide in the next phase. It will prepare its machineries, the metabolites, enzymes and all, so that in the next phase it will start dividing. As a result, the bacteria gradually increase in size and the bacteria attains its maximum size at the end of the lag phase. This is MCQ what is frequently asked. At the end of the lag phase, the bacteria attains its maximum size. Next is the log phase. Log phase is a phase where the bacteria divides exponentially. The bacteria divides exponentially. However, it is smaller in size. It is the most active phase of the bacterial growth curve, and this is the best phase for demonstrating the gram stain, because the bacteria will be uniformly stained and also it is biochemically active in log phase. So please remember, log phase is a phase where we have to do the staining method or the biochemical reaction, because it is the most active stage where it is uniformly stained and it is biochemically active. Followed by there is a stationary phase, and in this phase the bacteria divides as well as the bacteria start dying, hence the total number is constant. And in this phase bacteria form various structures like storage granules are formed in stationary phase, sporulation occurs in stationary phase, bacteria forms bacteriocin, and there are certain bacteria that can produce antibiotics also, penicillin and vancomycin. There are various antibiotics can be produced by bacteria, and all those antibiotics are produced in stationary phase. And after some time the bacteria enters into the decline phase of growth curve, where it doesn't divide, it only dies. Hence the number falls down. The viable number falls down. Okay, and in this phase, in the decline phase, involution forms are seen. Involution forms are seen in stationary phase, in decline phase. Involution forms are nothing but they are the aberrant or the irregular form of bacteria which are formed just before the death of the bacteria, and usually it is in the decline phase of growth curve. And gonococcus and Yersinia pestis are the example where the involution forms are more common. Gonococcus and Yersinia pestis. So this is all about bacterial growth curve. Then I will tell you about the various factors which is responsible for physiology of bacteria. Factors responsible for bacterial physiology. Let us discuss about the oxygen requirement. Based upon the oxygen requirement, you can classify the bacteria into obligate aerobe, obligate anaerobe, then microaerophilic, aerotolerant, facultative anaerobe, facultative aerobe. Like that there are 6 categories. Obligate aerobe, oxygen is lethal. Bacteria cannot grow on in presence of oxygen. Various examples are there like Pseudomonas, Mycobacterium tuberculosis, Brucella, then Bacillus anthracis, Nocardia. All these are example of obligate aerobe where oxygen is lethal. It grows in presence of oxygen. It grows in presence of oxygen. Oxygen is must. In contrast, obligate anaerobe where oxygen is lethal. Oxygen is lethal, and here bacteria cannot grow in presence of oxygen. Here the example is Clostridium. In contrast, aerotolerant anaerobe are the anaerobe which can grow in presence of oxygen, but it does not utilize the oxygen. It can grow in presence of oxygen for some time, but it doesn't utilize the oxygen, and here the example is Clostridium histolyticum. Clostridium histolyticum. Microaerophilic, they require 5 to 10% of oxygen. Example is Helicobacter and Campylobacter, as well as Mycobacterium bovis. These are example of microaerophilic organism which require 5 to 10% of oxygen. Facultative anaerobe and aerobe. Facultative anaerobe is an aerobe which can also grow anaerobically. And most of the pathogenic organisms like E. coli, Enterobacteriaceae, other organisms, Staphylococcus, Streptococcus, most of the pathogenic organisms are facultative anaerobe, which are actually aerobe but which can also grow anaerobically. In contrast, facultative aerobes are anaerobe which can also grow aerobically. Example is Lactobacilli. Lactobacilli are anaerobes which can also grow aerobically. They are example of facultative aerobes. So these are the various organisms classified based upon their oxygen requirement. Okay, so this is all about oxygen requirement. Apart from that, there are other factors that can affect the physiology of bacteria like carbon dioxide. Those organisms are called as capnophilic organisms like pneumococcus, H. influenza and all. Then temperature requirement based upon which you can classify the organism into psychrophilic, mesophilic and thermophilic. Okay, most of the pathogenic organisms are mesophilic, which can grow in and around body temperature. Okay, so these are the various factors required for physiology of bacteria. Now we'll discuss about bacterial pathogenesis, in which first we'll discuss about infective dose. Infective dose is the minimum dose required for causing the disease. A minimum load of the organism required for disease manifestation. The infective dose is usually low for Shigella and enteroinvasive E. coli and enterohemorrhagic E. coli, Entamoeba histolytica, Giardia. All these the infective dose is low. In contrast, there is high infective dose required for Salmonella and Vibrio. They say that Shigella, the infective dose is 10 to 100 organism, around 10 organism for Shigella, 10 to 3 to 6 organism is the infective dose for Salmonella, whereas for Vibrio it is 10 to 6 to 8. The high infective dose of Vibrio can be explained because of the reason that it is acid labile and it has to bypass the gastric barrier to reach the intestine. Now a bit about bacterial toxins. Bacterial toxins can be classified as endotoxin and exotoxin. endotoxin are lipopolysaccharide in nature in contrast to exotoxin which are proteinaceous in nature. Exotoxins are secreted outside, whereas endotoxin is a part of bacterial cell wall. Okay, exotoxins are heat labile, they are highly antigenic, they can be toxoided, and they have specific action. Enzymatic, they are enzymatic in nature, and each exotoxin has specific action. In contrast, endotoxin of all the bacteria, they are similar in function. Exotoxin of each and every exotoxin has a specific enzymatic action, whereas in general all LPS or all endotoxins, they are similar in action, they are heat stable, they are less antigenic. Okay, so these are the differences. Now I will tell you the various exotoxins and the mechanism of action. The exotoxins can be classified based upon their mechanism of action, such as inhibition of protein synthesis. Protein synthesis can be inhibited by two methods. By inhibiting the elongation factor 2. This is seen by diphtheria toxin and Pseudomonas exotoxin A. Protein synthesis can also be inhibited by inhibiting ribosome. This is seen by verocytotoxin and cigatoxin. Verocytotoxin is produced by enterohemorrhagic E. coli and cigatoxin inhibiting the ribosome. Toxin that activates cyclic AMP. This is examples are cholera toxin, heat labile toxin of E. coli, anthrax edema factor, and pertussis toxin. Pertussis toxin. All these are the toxins that activate cyclic AMP. Toxin that activates cyclic GMP is heat stable toxin of E. coli. Heat stable toxin of E. coli. Then toxin that act on nervous system, neurotoxins. Neurotoxins examples are botulinum toxin and tetanus toxin. Botulinum toxin, they say that for muscle contraction, you have a positive stimulus provided by acetylcholine. You have a negative stimulus for muscle contraction provided by glycine and GABA. Glycine and GABA. Botulinum toxin inhibits the release of ACH. Botulinum toxin inhibits the release of ACH. That leads to flaccid contraction of the muscle. In contrast, tetanus toxin inhibits the negative stimulated, that is glycine and GABA, that leads to spastic muscle contraction. So these are the two important examples of neurotoxin. Then toxin that act as super antigen, that is they activate T cells polyclonally. Polyclonal activation of T cells by binding to variable beta receptor of T cell receptor. They activate T cells polyclonally by binding to variable beta receptor of T cell receptor. Such toxins are staphylococcal toxin, like staphylococcal enterotoxin, toxic shock syndrome toxin, and streptococcal toxin, that is Streptococcus pyrogenic exotoxin A, B, and C. So these are the example of toxins that act as super antigen. Fine. Good morning. So coming to sterilization, this is the most important chapter in general microbiology. So coming to the definitions, sterilization is defined as killing of all microorganisms, including spores, and there should be a reduction of 10 to the 6 log colony forming unit of organisms. At least this much organism reduction should take place. In contrast, disinfection is defined as killing of all microorganisms excluding spores, and here the reduction of organism will be around 10 to the 3 log colony forming unit of organism. So these are the two distinctions what you have to remember. Other important entities will be asepsis, which will be killing of the pathogenic organism on the surface of the body, skin or mucosal surface of the body. This is called as asepsis. Decontamination is killing of organism up to or removal of organism from the floor or maybe equipments so that they are safe to handle. Okay, so these are the four different entities you should be remembering. So coming to the classification, the various methods that is employed for bringing out sterilization and disinfection. So methods can be classified as physical method and chemical method. Physical method, it could be heat sterilization, which could be either moist heat or dry heat. It could be filtration. It could be radiation. Okay, so these are the various methods under physical methods. Heat sterilization, they usually ask the mechanism of killing of organism. They say that moist heat kills by protein denaturation. Protein coagulation. Whereas dry heat, the mechanism of destruction is the code itself, which stands for charring, oxidative damage and elevated electrolyte. So this is the mechanism of killing of dry heat. So coming to the various methods under dry heat and moist heat. Dry heat, there are various methods are there. The most important is hot air-oven. Apart from that, other methods of dry heat like incineration and other less capable methods, less efficient methods like sun rays, flaming, drying, all these are other less capable methods. So hot air oven is the most important method under dry heat. Here the MCQ what they ask mostly confined to what are the material that can be sterilized under hot air oven. So most of the materials which are destroyed by moist heat, they are subjected to sterilization by dry heat. For example, all the glass items like glass flask, glass slides, glass syringes, glass bottles. So glass items are destroyed by autoclave, that is by moist heat. Hence they are sterilized by hot air oven. Apart from that, liquid paraffin, then oil, grease, glycerol. All these are various other methods that can be sterilized by hot air oven. Second MCQ, what they ask, what is the indicator? The biological indicator of sterilization is, for hot air oven we use Clostridium titani. The spores of Clostridium titani is used as biological indicator for sterilization. What is the temperature to be maintained? Hot air oven 160 degrees centigrade for 2 hours. This is the temperature to be maintained for hot air oven. Coming to various methods of moist heat. Moist heat, it could be less than 100 degrees centigrade, more than 100 degrees centigrade, and at 100 degrees centigrade. Okay? So less than 100 degrees centigrade, the various methods are, first is pasteurization. Pasteurization is usually done for milk. There are two methods, Holder's method and Flask method. Holder methods provides a temperature of 63 degree centigrade for 20 minutes. Whereas Flask method 72 degree centigrade for 15 to 20 seconds. Okay? And please remember, it is not, especially the Holder method is not useful, not effective for Coxiella burnetii. Coxiella burnetii. So this is one method of moist heat less than 100 degrees centigrade. Apart from that, other methods like water bath or vaccine bath, which is usually applicable for disinfection of vaccines. This is used for 1 hour, 60 degrees centigrade for 1 hour, vaccine bath. Then one more method is called as inspication. Inspication is less than 100 degree, that is approximately 80 degree centigrade for 20 minutes for 3 consecutive days. So this is the temperature to maintain 80 degrees centigrade for 20 minutes for 3 consecutive days. This is useful for egg and serum containing medium which will be destroyed by higher temperature. So egg containing medium like Algae medium, roadside egg medium, serum containing medium like low fluorescence serum sloop. So these are the media that should be disinfected by inspication. So coming to the methods of moist heat at 100 degrees centigrade. At 100 degrees centigrade, it could be boiling, steaming, and third is tyndallization. Tyndallization is nothing but it is 100 degrees centigrade, applying 100 degrees centigrade for 20 minutes for 3 consecutive days. It is almost same like inspiration, only thing is the temperature is different. It is 100 degrees centigrade for 20 minutes for 3 consecutive days. This is also useful for gelatin and serum containing medium. Gelatin and serum or sugar containing media, they are sterilized by tyndallization. They are sterilized by tyndallization. Fine. So this is all about at 100 degrees. Then above 100 degree centigrade, the one and only example is autoclave. This is one of the excellent method of sterilization. And here the temperature to maintain is 121 degrees centigrade for 15 minutes at 15 psi pressure. So this is the most recommended temperature for autoclave, 121 for 15 minutes for 15 psi pressure. And This is useful. Autoclave is used for sterilization of most of the microbiological culture media, which can withstand higher temperature. Biological control of sterilization for autoclave is Bacillus stearothermophilus. Bacillus stearothermophilus. This is the biological control for autoclave. Okay, so this is all about the heat sterilization. Coming to filtration. Filtration is useful. The indication of filtration is it is usually done for heat labile substances. All sort of heat labile substances like serum, sugar, toxin, antibiotic, vaccine, as well as to separate the viruses from bacteria. To separate the viruses from bacteria. So all these are the indication of filtration. There are two filtration methods are available broadly, categorized into depth filters and membrane filters. Depth filters are those filters, those with they will remove the particles throughout the depth of the filters. Okay, so when a liquid media is allowed to cross through a depth filter, the microorganisms are held back throughout the depth of the filter. In contrast, membrane filter are those that will restrict the microorganism only at the surface, not throughout the depth of the membrane. Depth filters are usually used in industrial applications. They have mostly industrial application. And various examples are there like candle filters, seeds filters. All these are previously used filters and mainly they were used for industrial application. In contrast, membrane filters are the most recommended filters for bacterial filtration. And usually they are composed of various membranes like cellulose membrane, polyvinyl membrane. All these are the various type of membrane which are available, and the average pore diameter is around 0.22 micrometer for the membranes. And there are two variations in the membrane filters. There are two special type of membrane filters. Those are examples are HEPA filter and ALPA filter. HEPA filter is high efficiency particulate air filter. High efficiency particulate air filter. It can remove 99.97% of organism having a diameter of more than 0.3 micrometer, whereas ALPA filter is ultra low particulate air filter, and it has a capability of removing almost 99.99% of organism having a diameter of more than 0.12 micrometer, having a diameter of 0.12 micrometer. Okay, so this is the cutoff for HEPA filters, and this is the cutoff for ALPA filters. So these HEPA and ALPA filters are usually they are applied for the filtration of air. Okay, for air filtration, HEPA and alpha filters are used. Okay, 1 second. HEPA stands for high efficiency particulate air. Alpha stands for ultra low particulate air filtration. Okay, so this is all about filtration. Then we can discuss about radiation. Radiation are of two types: ionizing radiation and non-ionizing radiation. Non-ionizing radiation are examples are ultraviolet ray and infrared rays. The UV rays, they are used for the disinfection of operation theatres, ward, etc. or any open space disinfection. Okay, they have low penetrating power and they are usually used for disinfection of operation theatre, ward and open space, as well as the disinfection of laminar wood where the microbiological work will be going on. For that disinfection also ultraviolet rays are used. Infrared ray, the ionizing radiations examples are cobalt rays, X-ray, cosmic rays, etc. Gamma rays, cobalt rays, the example is, it's an example of gamma rays. So all these are example of ionizing radiation, and the mechanism is they break the DNA without raise of any temperature. There is no temperature raise in ionizing radiation, hence it is also called as cold sterilization. It is also called as cold sterilization. Because there is no temperature raise, hence it is the ideal method for sterilization of heat labile substances like candid sutures, plastic syringes or any other plastic material, adhesive dressing material, plastic adhesive dressing material, all these which are heat labile, those can be sterilized by ionizing radiation. So coming to the chemical methods or the disinfectants. Disinfectants can be classified based upon the mechanism of action into low level disinfectant, intermediate level disinfectant, high level disinfectant, and chemical sterilant. So this classification is based on which organisms they are going to kill. The low level disinfectant, they can kill. Before I describe this, I can tell you the decreasing order of microorganisms based upon their resistance to be killed by disinfectants. Highest resistant organisms are, structures are prions, followed by Cryptosporidium oocyst, followed by the other oocyst, other coccidian oocyst, other coccidian parasite oocyst. Then you have bacterial spores, followed by you have Mycobacterium tuberculosis. Then you have fungi, then unenveloped viruses, then ordinary bacteria and ordinary enveloped viruses. Ordinary bacteria also gram negative are more resistant than gram positive. Okay, so this is the order. Prions are the highest resistant structures, followed by Cryptosporidium oocyst, other coccidian oocyst, then bacterial spores, then Mycobacterium tuberculosis, fungi, unenveloped viruses, then bacteria, their gram negatives more than gram positive, then followed by enveloped viruses. So the low level disinfectants, they are capable of killing the ordinary viruses and bacteria. However, they cannot kill other structures. Fungi will be plus minus, and mycobacterium spores and all the other structures, they are not able to kill. Intermediate level disinfectants, they can kill all, like low level, plus they can also kill Mycobacterium tuberculosis. Okay, high level disinfectants, they can also kill spores, and chemical stalin, they can also kill the other structures like the Cryptosporidium oocyst and prions. Prions are considered as highest level disinfectant. Prions are considered as highest level disinfectant and highest resistant to disinfectant, and they can be killed by various extreme of mechanisms, like for example autoclaving for 134 degrees centigrade for 1 hour, or maybe applying sodium hydroxide for 1 to 2 hours, or maybe sodium hypochlorite for again 1 to 2 hours. So these are the various extreme of mechanisms to denaturate, destroy the prions. So coming to some of the disinfectants and their important role, I can summarize what are the sporicidal agents. There are various disinfectants which can kill the spores, and the sporicidal agents can, the examples are, abbreviation is there, EFGH stands for ethylene oxide, formaldehyde, glutaraldehyde, and hypochlorite hydrogen peroxide. Hypochlorite will be plus minus, but hydrogen peroxide will always kill the spores. Apart from that, 3P stands for per-acetic acid, then orthophthaldehyde, which is commonly abbreviated as OPA, and plasma sterilization. Apart from that, of course, the physical methods like autoclave and hot air oven also can kill the spores. So these are the various methods that can destroy the spores. Okay, so some of the disinfectants we can discuss now. We can summarize the important features. Coming to alcohols, especially ethyl alcohol, they are used for hand hygiene purposes. Mainly they are used in hand rub and hand wash. Surgical spirit also contains ethyl alcohol. Isopropyl alcohol, the CDC recommends to use isopropyl alcohol for clinical thermometer disinfection. Disinfection of thermometer. Then formaldehyde is used for fumigation of operation theatre and other closed spaces. Apart from that, it is also used for preservation of anatomical specimens, preservation of organs and anatomical specimens. However, it is corrosive and it has a very pungent odor. All these are drawback of formaldehyde. But please remember, it is an excellent disinfectant. It is sporicidal and it is one of the chemical sterilant which can destroy almost all the structures. So because it is corrosive to the metal, hence formaldehyde is not recommended for the various sensitive metals like endoscopes. So for this purpose, the best method is glutaraldehyde. Glutaraldehyde is equally efficacious like formaldehyde, but it is less corrosive. Hence, it is best for endoscopes. The various endoscopes, cystoscopes, bronchoscopes, laryngoscopes, all these are better sterilized by glutaraldehyde. Glutaraldehyde, the usual concentration is 2%, but however now CDC recommends to use 2.4% glutaraldehyde. And the most commercial famous brand is Cydex. Glutaraldehyde has a drawback that it needs to be activated on opening of the bottle. The first time you have to activate the glutaraldehyde by alkalization. And once it is activated, it has to be used within 14 days. Otherwise, the efficacy will be destroyed. Hence, this is one of the important drawback of glutaraldehyde. So, to combat that, orthophthaldehyde is in use now. This is again more popular than glutaraldehyde. Nowadays, many hospitals they use OPA instead of glutaraldehyde for the same purpose, that is the disinfection of endoscopes. It is a better acceptable disinfectant than glutaraldehyde, and 0.55% concentration is mostly used. Okay, and it is the advantage of orthophthaldehyde is the activation is not required. The alkalization leading to its activation is there. What is there for glutaraldehyde? That step is not there for orthophthaldehyde. Something about plasma sterilization. This is something they ask. Plasma sterilization, there are 3 to 4 important components which you need to remember. This is again a process which will achieve chemical sterilization. It is an example of chemical sterilant. It can kill all the vegetative structures including the spores. And here hydrogen peroxide is used as a disinfectant. And the medium need to be vacuumed. Okay, and they say that plasma sterilization, again the control of sterilization is Bacillus stearothermophilus. Bacillus stearothermophilus. And another point to remember is here also the low temperature is maintained. Hence again heat labile substances which cannot be sterilized by autoclave, those can be put into plasma sterilization. Only drawback is it is quite expensive, hence it is not available in most of the places. Okay, but this is again an upcoming sterilization method which is frequently asked. Something about ethylene oxide. Ethylene oxide is also sporicidal. Yes, this is used, mainly it is used for sterilization of ventilated circuits. Yes, heart lung machine, dental equipments. Okay, all these are various parts which can be sterilized by ethylene oxide. Here also low temperature is been maintained around 55 degree centigrade for 4 hours. And ethylene oxide, again they say that it is carcinogenic. The drawback is it is carcinogenic as well as it is explosive. Okay, hence it is always mixed with hydrogen and helium and other inert gases to make it less explosive. So next we will discuss about the Spalding classification. Spalding has classified the various equipments and instruments in the hospital into various divisions. Like, it has classified the equipments into critical devices, semi-critical devices, and non-critical devices. Critical devices are those devices that will come in contact with the sterile environment, that will come in contact with the sterile environment of the body. So those examples are all the surgical items, all the surgical instruments, cardiac instruments, etc. And for the sterilization of critical device, always a chemical sterilant or a high level disinfectant is used. Semi-critical devices are those that comes in contact with mucous membrane. And here they say that here, examples of this will be the endoscopes, cystoscopes, laryngoscopes, etc. And here again a high level disinfectant is again used for sterilization. Whereas non-critical devices are those devices that will come in contact with intact skin, such as your stethoscopes, BP apparatus, etc. And here maybe a low level disinfectant will be enough. Okay, so this is Spalding classification, which is again in the hospital we use this classification to implement which disinfectant to use for which purpose. Okay, so this is again important for you. Then something about disinfection testing. There are three important methods of disinfectant testing. The most oldest and popular method is phenolic coefficient or Riedel-Walker test. This method, they say that it tests the efficacy of a disinfection. Usually it tests the efficacy of a phenolic group of disinfection by comparing the efficacy of phenol to Staph aureus, to Salmonella typhi. Here Salmonella typhi is used as organism against which the disinfectant is tested. Like there are various phenolic group of disinfectants that are there, like phenol, cresol, Lysol, etc. So any phenolic group of disinfectant, the efficacy against Salmonella typhi is tested by comparing that of phenol to Salmonella typhi. So if the phenolic coefficient is more than 1, the disinfectant is said to be satisfactory. Here the drawback of the Riedel-Walker test is, first is it can test only the phenolic group of a disinfection, because you are using phenol as standard, so you cannot compare with other class of disinfectant. Second drawback is it doesn't test the efficacy of the disinfectant in presence of organic matter. So in presence of organic matter, the disinfectant is working properly or not, that is done by a test called as Chick-Martin test. This test checks the efficacy of disinfectant to retain its efficacy in presence of organic matter. Various organic matter are there, like for example stool, blood, pus, yeast. All these are various organic matter. In presence of the organic matter, whether the disinfectant is able to retain its efficacy, that is tested by Chick-Martin test. The third test is the capacity test or Kelsey site test. Here the disinfectant, you are going to check the efficacy of the disinfectant. You are going to check the efficacy of the disinfectant or the capacity of the disinfectant. Capacity of the disinfectant to retain its efficacy when the microbiological load keeps increasing. Like for example, what you do is you take a big beaker with maybe 100 ml of a particular disinfectant. Then you keep on increasing the microbiological load. Keep on increasing the organism load. And this test checks the capacity of the disinfectant to retain its microbicidal efficacy when the organism load keeps increasing. So this is called as capacity test or Kelsey site test. And of course the last but not the least is in-use test. That is, this test checks the efficacy of the disinfection in real time. That is in the real time situation of the hospital, whether this disinfectant is able to produce the same efficacy or not. That is tested by in-use test. Okay, so these are the various method of disinfectant testing. So coming to the third chapter, culture media. What are the basic ingredients of a culture media? The basic ingredients of a culture media will be peptone, water, salt, and of course agar and meat extract. Agar is used as a solidifying agent. It is used as a solidifying agent, and please remember it doesn't have nutritive value. There is no nutritive value for agar. It doesn't provide nutrition to the medium. It is only used as a solidifying agent. So what are the various basic media examples? Basic media or simple media examples are peptone water broth, nutrient broth and nutrient agar. Peptone water broth has got peptone, salt and water. Nutrient broth is nothing but peptone water broth plus meat extract. And nutrient agar is nutrient broth plus agar. So it is a solid medium, whereas peptone water broth and nutrient broth are the liquid medium. And the role of the basal media, they help in demonstrating the non-fastidious nature of organism. So to demonstrate that the organism is fastidious or not, you have to use a basal medium, because if it is growing on a basal medium, it is said to be non-fastidious. Also used to demonstrate the bacterial pigment, and also the various biochemical reactions can be performed on basal media in a much better way. They say that basal media is the best media to demonstrate the catalase stage, oxidase stage and various other biochemical reactions. So other type of media, next is enriched media. Enriched media is basal media if you add various enriched substances like blood, serum, egg, then it becomes enriched in nature, so that it can support the fastidious organism also. Enriched medium, the fastidious organism also can be supported. Examples are blood agar, chocolate agar, low-flush serum slope, etc. Okay, chocolate agar is nothing but heated blood agar. It supports Haemophilus influenza, which is a highly fastidious organism. Okay. Next is enrichment broth and selective medium. Both, the basic definition is same. Enrichment broth and selective medium, the common definition is they support the pathogenic organism in the sample, whereas they inhibit the normal flora present in the sample. They inhibit the normal flora in the sample, whereas they support the pathogenic organism in the sample, because there is extra inhibitory substance which is added. So enrichment broth and selective medium, here you add an extra inhibitory substance so that it will inhibit the other organisms and only support the pathogen or the wanted organism present in the clinical sample. So this is a common definition. The difference is enrichment broth is a liquid medium, whereas selective medium is a solid medium. Otherwise the definition is same. Example of enrichment broth: alkaline peptone water broth for Vibrio, alkaline peptone water broth, Mansour's broth. This is also for Vibrio. Okay. Similarly, selenite F broth, gram negative broth, and tetrathianate broth. Selenite F broth, gram negative broth, and tetrathianate broth, all these three are used for Salmonella and Shigella. For Salmonella and Shigella. Okay? Example of selective medium are plenty. Selective medium examples are plenty. TCBS and Mansour's medium, all these are for Vibrio. Then the Lowenstein-Jensen medium for Mycobacterium tuberculosis, Wilson-Blair medium for Salmonella, DCA deoxycholate citrate agar, XLD, all these for Shigella and Salmonella. Okay, so these are the various selective media. There are so many other media also, you can have a look. It is given in detail in your book. Okay, transport media. It is used for transportation of the sample from the site of collection to the microbiology lab. And please remember, bacteria do not multiply in transport media. It is only used for transportation of the specimen, but bacteria usually do not multiply in transport medium. Examples are Pike's medium for Streptococcus, okay, Stewart's medium, and Amis medium for Gonococcus, Venkatraman Ramakrishnan medium, Carey Blair medium, this is for Vibrio. Okay, so like that there are various transport medium which can be asked in the exam. Fine. Next is differential medium. Differential medium are the media which can differentiate the bacteria into two groups based upon some specific property. Example is McConkey agar. McConkey agar, based on lactose fermentation, it divides or it can differentiate the bacteria into lactose fermenting bacteria which will produce pink colony and non-lactose fermenting bacteria which will produce colorless or pale colony. Even clade agar, that is cysteine lactose electrolyte deficient agar, is also an example of differential medium which has the same property, that is it can differentiate the gram negative bacteria into lactose fermenters and non-lactose fermenters. It is specifically used for culture of urine specimens. The advantage of clade agar over McConkey agar is it can also support the gram positive and yeast, whereas McConkey agar may not support gram positive and yeast, whereas clade agar can also support gram positive and yeast. Hence it is better than McConkey agar, especially for urine specimen. And they say that if you use clade agar, there is no need to use blood agar also, because it has an advantage over blood agar, that is it prevents proteus swarming. Blood agar, there is swarming of proteus, whereas in clade agar there is no swarming of proteus. It will prevent the swarming of proteus. So this is the advantage of clade agar over blood agar. So they say that for urine specimen, either you use a combination of blood agar and McConkey agar, otherwise you can just use clade agar, which can serve the purpose of both blood agar and McConkey agar. So that is why in the lab where the urine specimen sample load is very high, they prefer to use a clade agar alone than to use a combination of blood agar and McConkey agar. So these are the various type of media. Then the media used for anaerobic culture. Example is Robertson cooked broth meat extract. Robertson cooked meat broth, RCM broth, is for anaerobic sample. Neomycin blood agar. Then brain heart infusion agar supplement. Supplement like vitamin K, hemin. These two are used as a supplement. That is brain heart infusion agar with as for supplement such as vitamin K and hemin. All these are various anaerobic medium. Egg yolk agar. Egg yolk agar is another example of anaerobic medium. Similarly, medium used for blood culture. For blood culture, brain heart infusion agar and broth is used. Blood culture is done in blood culture bottles, and there are two type of blood culture bottle: monophagic and biphagic. Monophagic blood culture bottle will have only liquid medium, that is brain heart infusion broth, whereas biphagic blood culture bottles will have a solid slant and also liquid medium. The solid slant is brain heart infusion agar and the liquid medium is brain heart infusion broth. Okay, so monophagic and biphagic media that is used for blood culture bottle, they are nothing but composed of brain heart infusion broth and agar. The media used for antibiotic susceptibility test. For antibiotic susceptibility test, Muller-Hinton agar is used. MH. Muller-Hinton agar is used for antibiotic susceptibility test. Okay, so these are the various culture media. Now I will tell you the methods to create anaerobiosis. Anaerobiosis can be created by various ways, like for example by displacement of oxygen. This is done by McIntosh field jar. This is the old method, whereas the advanced method is by using a specific instrument called as enoxomat instrument, which can displace the oxygen and it will replace by adding hydrogen. Apart from that, by various chemical reaction to combust the oxygen, example is gas pack system. By using anaerobic glow box or a specialized media called as PRAS. PRAS media is nothing but it is a pre-reduced anaerobic sterilized medium. Pre-reduced anaerobic sterilized medium. This kind of media also is used to provide anaerobic environment. Fine. There are various culture methods, like for example, strict culture is used for culturing the sample, inoculating the sample in the various culture media. It is a routine method used for inoculating the specimen sample in various culture media. Strict culture. Lawn culture or carpet culture, this is used for antibiotic susceptibility test. Antibiotic susceptibility test on Muller Hind and agar lawn culture or carpet culture is used. Apart from that, there is other culture method like stroke culture, starch culture. All these are the starch culture is used for triple sugar and a medium. Mannitol motility medium. Stroke culture is used for citrate and urease medium. Okay, so there are various. In fact, in triple sugar ion test, a combination of scrap and stroke both is used. Okay, triple sugar ion test, both starch culture and stroke culture both are used combinedly. Okay, so these are the various culture methods available. Now I will tell you about the automated culture system. Automated culture system like BACTEC, Bacteria Alert, ESP system, MIGIT. All these are various automated culture system for bacterial culture. They will continuously monitor the bacterial growth automated fashion. BACTEC uses radiometric principle to detect the bacterial growth. Bacteria Alert uses fluorescent principle to detect the bacterial growth, whereas ESP system uses the manometry to detect the pressure difference, when the bacteria grows and produces the carbon dioxide. MIGIT is mycobacterial growth indicator tube. Mycobacterial growth indicator tube, it is used for growth and detection of Mycobacterium tuberculosis, and it is also based upon the fluorescent based principles. Okay, so these are the various automated culture systems available. Now I will tell you something about the molecular method, especially PCR, polymerase chain reaction. There are various molecular methods, and the most important is PCR or polymerase chain reaction, developed by Carey B. Mullis. And this is a method by which you can amplify a single copy of DNA into millions of copies. And PCR has got three basic steps. First is DNA extraction. Second step is amplification of the extracted DNA. Third is visualization of extracted DNA by doing a gel electrophoresis. DNA extraction, amplification of the extracted DNA, then visualization of the amplified DNA by doing gel electrophoresis. DNA extraction is done by various methods, by lysozyme method, proteinase K method, boiling. All these are various methods to extract the DNA. Once the DNA is extracted, of course you know that the bacterial DNA is double stranded DNA. So the next step is amplification step. It has got three basic components. First is denaturation, so that the double stranded DNA is separated into two single strands, and this is done at higher temperature, that is around 90 to 95 degrees centigrade, denaturation. Third is, second is annealing of primer. Annealing of primer. So primers are nothing but they are small nucleotide sequences complementary to the respective part of bacterial DNA. So you have to add the specific primers against the bacteria which you are suspecting in the clinical sample. So for example, if you are suspecting Haemophilus influenza DNA in CSF of a case of meningitis, so in such case you have to add specific H influenza primers. If you add a different primer, then the amplification will not take place. So annealing of the primer is the most specific step of a PCR. Okay, so primer will get annealed to the specific part of bacterial DNA. Third step is extension step. Extension step is done by adding DNA polymerase. By adding DNA polymerase, you have to add a specific type of DNA polymerase called as Taq polymerase. Taq polymerase is a DNA polymerase extracted from a plant called as Thermus aquaticus plant. Thermus aquaticus plant, and this Taq polymerase has the property of withstanding higher temperatures of a amplification cycle. So Taq polymerase is added, and this Taq polymerase, the role is it will keep on adding nucleotides. You also have to add a nucleotide to the medium. So you have to add Taq polymerase plus you have to add nucleotides. The role of the Taq polymerase is the Taq polymerase. What it will do is it will keep on adding the nucleotide at the growing end of the primer. It will keep on adding the nucleotide at the growing end of the primer, so that at the end of the extension step, you will produce two double stranded DNAs. So this is one step of amplification. This is one cycle of amplification. So like that, there are 30 to 35 cycles which will keep on going, so that at the end of the amplification there are millions of copies of amplicons which will be generated, and there are various modifications of PCR. First is reverse transcriptase PCR. PCR detects DNA or RNA? PCR amplifies the DNA. If you want to amplify the RNA, you have to do a reverse transcriptase PCR which will amplify the RNA. Similarly, the next PCR is multiplex PCR, where more than one primer of different organisms responsible for same clinical syndrome are added. So multiplex PCR is used for syndromic approach. For example, if you are suspecting meningitis, then you add multiplex then you do a multiplex PCR, where you can use more than one primer of common organisms of responsible for meningitis, like Haemophilus influenza, Pneumococcus, Meningococcus, all the common organisms, the respective primers you can add, so that whichever bacterial DNA is there in the clinical sample, the respective primer will anneal and will get amplified. So this is multiplex PCR, which is used for syndromic approach. Third is nested PCR, where it is a 2 round of PCR. Each round we use one primer each. So 2 primers are used, and to make 2 round of PCR, first you have to do a PCR round 1, where you are using primer 1, and the amplified product you are subjected to one more PCR by using a second primer, and both the second primer is targeted against the same organism but a different genetic sequence, so that it will increase the specificity of the reaction. And because it is a double round amplification, it is more sensitive than a conventional PCR also. But the problem of nested PCR is you are opening the vial multiple times, hence there is more risk of contamination. So this is a drawback of nested PCR. Otherwise it is highly specific because you are doubly checking the organism's DNA sequence by using two different primer targeting the same organism, and as well as it is highly sensitive because the amplified product of the first DNA is subjected to a second round of amplification, so that more amplicons are produced, hence it is highly sensitive also. Last but not the least is real-time PCR. PCR is the conventional PCR is quantitative or qualitative. Of course it is qualitative. The conventional PCR can detect only the presence or absence of DNA. It cannot say how much of DNA is there. So to quantify real-time PCR is done. Please remember, it is done for quantification. Hence it is useful for monitoring the response to treatment. Especially HIV, hepatitis B, it is useful for monitoring the response to antiretroviral drug in case of HIV. And please remember, here you are doing real-time visualization of amplification. Please remember, the basic difference between a conventional PCR and a real-time PCR is conventional PCR, you will know that amplification has taken place or not only after the end of gel electrophoresis. After that, if you can see the bands, then you can say that yes, amplification had taken place. Whereas in real-time PCR, while the amplification is going on, you can visualize the amplification at a real-time basis. That is why it is much faster than the conventional PCR. And of course, it is higher sensitive and higher specific than conventional PCR. And also there is less chance of contamination as compared to a conventional PCR. Hence, real-time PCR is the future of microbiology now. It is the most sophisticated molecular method which can be used for diagnostic microbiology. So this finishes this chapter. Next we will discuss about the bacterial genetics. Okay, 1.4 bacterial genetics. Bacterial genetics, first is we will discuss what are the various methods of gene transfer. Various methods of bacterial DNA transfer. The bacterial gene can be transferred by various methods, can be clubbed as transformation, transduction and conjugation. Transformation, transduction and bacterial conjugation. Transformation is a method of transfer of bacterial genes by agency of free DNA. They say that the free DNA produced after the bacterial death, they are uptaken by the surrounding bacteria. Okay, if the bacteria dies, the DNA will be released outside, which will be taken up by the surrounding bacteria. This is called as transformation. Just the free DNA will be taken up. And Griffith experiment, which was done in 1930s, this was done in mice for demonstrating the transformation of pneumococcus. And this is the Griffith experiment is done to demonstrate the transformation, and he has used mice and pneumococcus strains he has used to demonstrate the transformation. The transduction is the transfer of bacterial gene from one bacteria to other by the help of bacteriophages. You know that the bacteriophages are the viruses that infect a bacteria. So if this is a bacteria and if this is a bacterial chromosome, then there are certain bacteriophages that can infect a bacteria. So a bacteriophage, when they infect a bacteria, the phage DNA goes inside and it gets integrated with the bacterial DNA. So this is called as lysogenic conversion. This is called as lysogenic conversion. That is, the phase DNA goes inside the bacterial cell and it gets integrated with the bacterial DNA. So in this case, when the phase DNA is detached, after some time the phase DNA gets detached to come to the cytoplasm. So when the phase DNA is detached, it may take the adjacent bacterial DNA along with it. Okay, so when the phase DNA gets detached, it may take the adjacent bacterial DNA along with it. Such phase DNA, when it infects another bacterial cell, then it gets integrated with the bacterial chromosome, so that the bacterial DNA from the first cell can go to the second cell. So this is called as transduction, by which the transfer of bacterial DNA from one bacteria to other bacteria by help of bacteriophage. And transduction is of two types: generalized transduction and restricted transduction. Restricted transduction is the method by which the phage takes up the adjacent DNA. Okay, only the adjacent DNA if the phage will take up, it is called as restricted transduction. Whereas generalized transduction is a method by which the phage can take up any DNA from the bacterial chromosome. Any DNA, maybe from any site, the part of the DNA can be taken up by the bacteriophage. This is called a generalized transduction. One more variety is lysogenic conversion. Lysogenic conversion, as I told you, this is a method by which the phage DNA, this is a bacteriophage, so the phage will infect the bacteria and the phage DNA gets integrated with the bacterial chromosome. This is called as lysogenic conversion. I have already explained you. And in this case, the phage DNA being foreign in nature, it may gives the various property to the bacteria, and one of the important properties is toxigenicity. Please remember, there are various phage coded toxins which impart toxigenicity to the bacteria. I have already explained you earlier. They are abbreviated as A, B, C, D, E. Like A and C, toxin of Streptococcus pyrogenic exotoxin A and C, Streptococcus pyrogenic exotoxin A and C, botulinum toxin C and D, cholera toxin, diphtheria toxin, and enterohemorrhagic E. coli virocytotoxin. Enterohemorrhagic E. coli virocytotoxin. So please remember, there are 5 toxins which are coded by bacteriophage, and during the lysogenic conversion stage, the bacteriophage coded toxins impact toxigenicity property to the bacteria. So this is called as lysogenic conversion. Now I will tell you about bacterial conjugation. Conjugation is a method by transfer of bacterial DNA from one bacteria to other by the formation of conjugation tube. And the conjugation tube which is formed, it is coated by a plasmid called as F factor. Okay, and bacteria which carries F factor, they are called as F plus or male bacteria. They are the bacteria which carries F factor, and F factor is nothing but it is a plasmid which codes for the conjugation tube. F factor is a plasmid which codes for the conjugation tube. So such F plus or male bacteria, when it comes close with another bacteria which is lacking the F factor, F minus bacteria, only the chromosome will be there, but there is no plasmid outside. So F minus bacteria, when they come close with F plus bacteria, the F factor forms the conjugation tube. First the F factor forms the conjugation tube. Then second step is the F factor gets multiplied, duplicated, and the third step is a copy of F factor goes to the female bacteria. So after the conjugation is over, F minus bacteria gets converted to F plus bacteria, because F minus bacteria attains the F factor and it becomes F plus bacteria. So this is the usual method of bacterial conjugation. And along with F factor, if certain other resistance gene or certain other virulent genes can also go to the recipient bacteria. Okay, so if only F factor goes, then F minus cell will become F plus cell. Along with F factor, if certain virulent gene or certain drug resistant gene, if it goes to the female bacteria, then along with attaining the F factor, it also attains the resistant genes as well as the virulent genes. So bacterial conjugation is a method by which we can transfer the genes from one bacteria to other bacteria by the formation of conjugation tube. Okay. Next is, what is HFR state? So here I want to explain you that this is bacterial chromosome and this is F factor. Sometimes what happens is the F plasmid gets integrated with the bacterial chromosome. Sometimes the F plasmid gets integrated with the bacterial chromosome. This state is called as HFR state, high frequency recombination state. Wow, high frequency recombination state. The meaning of this is, when a female bacterium having only the chromosome comes close to a HFR cell, HFR bacteria, then this is a state where the recombination occurs more frequently. There is more chance of formation of the conjugation tube. F factor will form the conjugation tube and the frequency of recombination is more. But the problem is, because it is in an integrated stage, so when F factor gets duplicated and a copy of F factor goes to the female bacterium, and it takes a longer time to complete the procedure because the F factor is in an integrated state. So before the procedure is completed, often the conjugation tube is broken. Before the F factor completely goes to the F minus cell, often the conjugation tube is broken. Hence, they say that the F minus cell, usually they are not able to become F plus cell in HFR state. So please remember, HFR state is a state where F factor is in the integrated form with the bacterial chromosome, and in this state the chance of the frequency of recombination between the cell is more. Hence it is called as high frequency recombination state. However, though the frequency of recombination is more, the F factor does not go completely to the recipient cell. Hence, the F minus cell, usually they do not become F plus cell. So this is the meaning of HFR state, high frequency recombination state. Next is, what is F des cell? What is F des cell? F des means what? This is the HFR state, this is the bacterial chromosome and this is the F factor. So this is a HFR state. After some time, the F factor will be detached from the bacterial chromosome. F factor will be detached from the bacterial chromosome and it will come to the cytoplasm. So when F factor, from a HFR state, when the F factor gets detached and comes to the cytoplasm, it may carry the adjacent bacterial genes, adjacent chromosomal genes along with it. This state is called as F des state. F des state. It is a state where F factor comes back to the cytoplasm. Along with it, it carries a certain bacterial chromosomes along with this. Such F des bacteria, when it comes close contact with the F minus bacteria, then what happens? The F factor forms the conjugation tube and the entire thing gets duplicated along with the bacterial chromosome, along with the chromosomal gene. the entire thing gets duplicated and a copy goes to the female bacteria, so that at the end of conjugation the F factor goes, along with that the bacterial genes also they go to the female bacteria. And many of these bacterial genes may be the virulent gene or maybe the drug resistant gene also. So please remember, when a F dash cell meet with F minus cell, the resultant cell will be a F dash cell, because it will have the resultant recipient cell will have F factor as well as it will have bacterial genes also surrounding to it. So the recipient cell actually will receive at F dash factor. Hence the recipient cell will become F dash cell. So please remember, I want to conclude here by saying that when F plus cell met with F minus cell, the resultant recipient will be F plus. When a HFR state met with F minus cell, the mating is more frequent. However, the resultant cell remains F minus only. When a F dash cell met with F minus cell, when F dash cell met with F minus cell, the resultant cell will be F dash. Okay? So the resultant recipient will be F dash. So these are the three important outcome of conjugation what you need to remember. It is very, very important. You will get confused in the exam. Okay? So this is all about bacterial conjugation. Now I will tell you a bit about transposons. Transposons, they are discovered by Barbara McClintock. And transposons are also called as jumping genes. They usually jump between the bacterial chromosome and plasmids. They are the jumping genes. They usually jump between the bacterial chromosome and plasmids. So if this is a bacteria, this is a bacterial chromosome and these are the plasmids. Then transposons are the small genetic elements, very small genetic elements, very small genetic elements. Sometimes they are present on the bacterial chromosome. Sometimes they jump to become a part of bacterial plasmid. So they usually jump between the chromosome and the plasmid, and they differ from plasmid by the way that they do not have independent replication. They do not have independent replication. If the transposons are outside, they cannot replicate by themselves. They can replicate only when they are integrated to bacterial chromosome or they are integrated to plasmid. So they do not have bacterial replication. They do not have independent replication. So transposons also they have importance in bacterial drug resistance. They say that the various drug resistance genes are coded by transposons. Okay, so this is all about transposons. Okay. Now I will tell you the various methods of bacterial drug resistance. There are various methods of bacterial drug resistance. Bacterial drug resistance first is by efflux pump mechanism. This is the mechanism by which the drugs are transported out. They say that in the bacterial cell membrane there are various efflux pumps, and the role of efflux pump is whichever antibiotic will come inside, once the antibiotics will come inside, they are transported out immediately by the efflux pump. This is one mechanism. Second mechanism is by producing various enzymes, like for example beta lactamases, or by producing aminoglycoside modifying enzymes. Third mechanism is by alteration of target site. Alteration of target site of the drugs. This is shown by various strain like MRSA, VRSA, VRE. All these are various organisms, various bacteria which exhibit drug resistance by alteration of target site. For example, in MRSA, the target site of beta-lactam antibiotic, you all know, the target site of beta-lactam antibiotic is the penicillin binding protein. Penicillin binding protein are the target site of beta-lactam antibiotic present on the bacterial cell wall. The penicillin binding protein gets altered to penicillin binding protein 2A, and this altered protein has got less affinity for beta-lactam antibiotics. So MRSA are resistant to all beta-lactam antibiotic, and this is because they undergo alteration of the target site for beta-lactam, that is the penicillin binding protein, gets altered to penicillin binding protein 2A. Similarly, VRSA again, VRSA and VRE, the mechanism is same. It is due to VAN gene. And VAN gene, what it does, it alters the target site of vancomycin. The target site of vancomycin is D-alanine sequence, which is present in the bacterial cell wall. It is a peptidoglycan side chain D-alanine, which is present in the bacterial peptidoglycan layer. This gets altered to D-alanine D-lactate or D-alanine D-serine. This altered protein has less affinity for vancomycin. So this is a mechanism shown by VAN gene, and VAN gene is expressed by VRE, that is vancomycin resistant enterococcus, and VRSA, that is vancomycin resistant staphylococcus aureus. So all these are the various mechanisms by which alteration of the target site is the principal mechanism of bacterial drug resistance. Okay, now I will tell you about something about beta-lactamases. According to Ambler classification, the beta-lactamases can be classified into 4 groups. ESBL, that is extended spectrum beta-lactamase. MBL, that is metallo-beta-lactamase. MC beta-lactamase, and the last one is oxacilinase. This is not very important, but the first 3 are very important for example. Extended spectrum beta-lactamase, if the bacteria produces extended spectrum beta-lactamase enzyme, then it is resistant to all penicillin plus first, second, third generation cephalosporin. All penicillin plus first, second, third generation cephalosporin. However, this resistance can overcome by adding beta lactamase inhibitor. For example, the clavulanic acid or sulbactam. If you add beta lactamase inhibitor like clavulanic acid or sulbactam, this resistance can be overcome. Next is AMC beta lactamase. AMC beta lactamase, the spectrum is ESBL spectrum plus in addition it is resistant to cefamycins like cefoxitin and cefotitan. Cefamycins like cefoxitin and cefotitan. Plus all the range of ESBL organisms also, ESBL spectrum of antibiotics also AMC will be resistant. And the peculiar is it is not overcome by adding beta lactamase inhibitor. Please remember, addition of beta lactamase inhibitor is of no use. the resistance, the AMC resistance is not overcome by addition of beta-lactamase inhibitor. Next is metallo-beta-lactamases. Metallo-beta-lactamase, the spectrum is AMC spectrum plus in addition it is resistant to carbapenems like meropenem and imipenem. And this resistance also is not overcome by addition of beta-lactamase inhibitor. So please remember, metallo-beta-lactamases are resistant to AMC spectrum plus carbapenem and it is not overcome by addition of beta-lactamase inhibitor. Okay, so in this context what they can ask is, for ESBL producers, the treatment option if they ask, for ESBL producer the treatment option is you can give cefamycin, cefoxitin can be given, carbapenem also can be given, or other class can be given. Cefoxitin can be given, carbapenem can be given, or other class like for example aminoglycoside can be given. Whereas the treatment option for AMC beta-lactamase is either carbapenem or other class. ESBL, one more treatment option is you can give penicillin or cephalosporin plus adding a beta-lactamase inhibitor. You can add penicillin or cephalosporin, any of the spectrum can be given, plus you can add beta-lactamase inhibitor. Whereas beta-lactamase inhibitor is not useful for AMC, you can give only carbapenems or other class for AMC beta-lactamases. Whereas for metallo-beta-lactamases, no beta-lactam can be given. The only treatment option is other class of antibiotic can be given like aminoglycoside. So please remember, there are 4 treatment options for ESBL. First is cefamycin, second is carbapenem, third is penicillin or cephalosporin adding beta-lactamase inhibitor, or fourth is other class. For AMC beta-lactamase, you can give either carbapenem or other class. You cannot add a beta-lactamase inhibitor. For metallo-beta-lactamases, the only treatment option is other class like aminoglycoside or any other class of antibiotic, but beta-lactamase inhibitors you cannot give, or any of the beta-lactamase including the carbapenems will not be effective because they are resistant. Okay, so that finishes bacterial drug resistance.